Hi, this video based on relativistic effect on lifetime of particle. That is Unit 4, Edexcel IAL Unit 4 Particle Physics. Before watching this video, see the description of this video. I have already done complete lesson on particle physics, complete lesson on magnetism, complete lesson on circular motion, and different 12 lessons on electric field. The link or URL for all those videos are given in the description of this video, so you can follow those lessons also. Also, by using the playlist of this channel, you can navigate to any video you require. Playlist of the channel means when you watch this video, on the left side little down there is a red color icon for my channel. If you touch it, you'll go to the channel directly. There you can see the playlist. From playlist you can select any video related to unit 1, unit 2, unit 3 and past papers also. Okay, so the relativistic effect on lifetime of particle. Based on this question appears 4 different years. The first one I can say that is in October 2022. October 2022. Question 13C. Question 13C. Same way, January 2022. Question 17. D part 3. Same way, October 2021. Question 16. C. Then the final thing, January 2021. Question 14A. Okay, so the answers are the same for these questions. Before telling the question, the marks for this question, October 2022, question 13C, that is the marks, 2 marks given for that question. So there are 2 marks is given for that question. Here January 2022, that also 2 marks. October 2021, that is 3 marks. And January 2021, they allocated 5 marks. Okay, so the question is like this. All questions are similar actually. What they say, when muon is created in laboratory, when it is at rest, so laboratory means in laboratory, muon, you know muon is a fundamental particle, it's a lepton. When muon is created and when the muon is almost at rest or when it is moving at very lower speed, its lifetime is lower. But when it moves at higher speed, something like almost closer to speed of light, or something like 0.7 times of speed of light or 0.9 times of speed of light, it is able to survive longer. That means its lifetime becomes longer. How is it possible? That's the question comes. I'll read the question quickly. October 2022, question 13C. It's about a boson. A Z bosons produced by high energy collisions can have a range of lifetimes. The Z bosons with the longest lifetimes are those that were moving very fast. Explain this observation. That means the Z bosons, right? We know them. We don't much deal about bosons, but anyway, Z bosons, they have a range of lifetimes, but what they are saying, the Z bosons with longest lifetimes are those that were moving very fast. So the answer is very simple. The same answer given for all these 3 questions. I'll read the question 2022. That is, stationary muons are unstable and have a mean lifetime of few microseconds, very small lifetime. That means they will decay again into energy. Explain why muons in the ring are observed, it's a ring accelerator. Ring are observed to have much greater mean lifetime. That means the muon is moving in a ring accelerator at very high speed. How is it possible Explain why muons in the ring, ring means ring accelerators, are observed to have a much greater mean lifetime. That is the January 2022 question. Then October 2021 question, most of the particles detected in the spark chamber are muons. The muons were created in the upper atmosphere. Muons normally have a very short lifetime and should have decayed before they reach the surface of the earth. Explain why these muons reach the surface of earth. So they are saying their lifetime is shorter. Most of the particles detected in the spark chamber are muons. The muons were created in the upper atmosphere. Muons normally have very short lifetime and should be decayed before they reach the surface of Earth. Explain why these muons reach the surface of Earth. Answer is the same. For the January 2021 question, 5 marks, but there we same question, but their numerical values are given. The speed of the muon is given 0.994 times of speed of light, and the distance is moving is given 1600 meter. Lifetime is given 2.2 10 to the power minus 6 seconds, that is 2.2 microseconds. So then they are asking, explain whether those observations are consistent. That means they are able to see the muons at the bottom of the mountain, which has height of 1600 meter. Okay, so students normally ask, what's the answer? The answers are the same for all different years. The questions only here, we need to do a calculation. That means the lifetime is given. We need to find the time taken to reach the bottom of the mountain, and we show that time is greater than the lifetime of the muon. Then we are going to use the same answer which is given in these 3 years. So that's the reason they are giving 5 marks in that question. Okay, so when you see the answers, all these 3 points are given. If it is a 2-mark question, only the first 2 points are given. If it is a question like how it is able to travel longer distance, then the 3rd point also given. If it is like a question related to how it is able to survive for longer time, then the first 2 marks are given. But if it is a question something related to how is it possible to travel longer distance, then the 3rd mark given for the 3rd statement. But here the 5 marks is given the additional 2 marks for the calculation. So they are giving the lifetime of the muon, which is 2.2 10 to the power minus 6 seconds. In this question, I am telling about this question, January 2021, 5 marks. So these 3 marks are given. So before writing these 3 statements, we have to do a calculation. So the height of the mountain is given 1600 meters, and the speed of the muon also given 0.994 c. So we need to find the time taken. If it is traveling at that speed, what could be the time taken by the particle? So time will be speed over distance. Sorry, speed equal distance over time, time equal distance over speed. So distance 1600 meters divided by 0.994 into 3 into 10 to the power 8. So if you solve this, the time that should taken by the muon to reach the bottom of the mountain, that time will be 5.37 10 to the power minus 6 seconds. So that will be 5.37 10 to the power minus 6 seconds, which is greater than the lifetime. The lifetime is given. The lifetime is given as T lifetime. I can say TL, that's a lifetime is given, which is given as 2.2 10 to the power minus 6 seconds. So if the muon wants to reach the ground from the top of the mountain, the required time is 5.37 10 to the power minus 6 seconds. That is greater than the lifetime 2.2 10 to the power minus 6 seconds. So it can't reach the ground. Before that it will decay into energy. But it reached the bottom. It was detected at the bottom of the mountain. Muons were detected. So how is it possible? Then after doing this question, they are giving 2 marks for this calculation. 2 marks for this calculation. Then you should compare. The time taken is longer, but it's able to reach the ground. Why? This is the 3 points you need to write. At the speeds close to speed of light, due to relativistic effect, the lifetime of the particle will increase. So the travel further than the expected. So that means it's able to reach the bottom. You can say it travels further than the normally expected, or the muon is able to reach the bottom. You have to give for the third point. So anyway, these are the answers. Normally you write similar answers, so it's not an issue. But students normally ask, not in your syllabus, you don't need to go in detail, but since students ask, I'm going to explain that also. Normally students, they ask about this point. Due to relativistic effect, lifetime of the particle increase. How that happens? Say the relativistic effect, normally the lifetime, when the particle is created in the laboratory and the particle is at rest, or maybe moving at very usual lower speeds, there the lifetime is 2.2 10 to the minus 6 seconds. But when it travels at speed of closer to speed of light, that is 0.994 times the speed of light, how is it increase? The lifetime increase. Most of the students, they ask to explain the second statement, how that is happening due to the relativistic effect, lifetime of the particle increase. How is it possible? The students ask. Anyway, in exam view, you don't need it. Actually, if you write this, you will get the full marks. But 4 times this question appeared in the past way. But sometimes students want to know, certain students. So for them only, I'm going to explain how the lifetime increases when the particle travels at longer time. So that cannot be explained by using classical physics. We need to use special theory of relativity, which was proposed by Albert Einstein. So actually, what is special theory of relativity? Actually, classical mechanics, so is it wrong? No, nothing wrong. Classical physics or classical mechanics, there's nothing wrong. But the special theory of relativity is more accurate when particles or any object travels at very high speed. So actually, special theory of relativity reveals our understanding related to particles, their mass, their energy, space and time when the particles travel at higher speed, which is closer to speed of light. So it reveals a clear understanding, or it reveals how the understanding of the theories related to space, time, mass and energy should be adjusted or slightly changed when something travels at higher speed, which is almost closer to speed of light. So I'm going to use the special theory of relativity, not in detail, very basic way, very simple way, such that an A-level student can understand. So I'm trying to explain it. But anyway, exam you don't need this explanation. These are enough for to get the full marks. Okay, so if I want to explain the time dilation, we need to introduce few simple technical words what we use in special theory of relativity. First thing is frame of reference. What is frame of reference means? You know that normally in unit 1, if the question says a car is traveling at a speed of 15 meter per second, means the speed is measured, or the velocity is measured relative to something else. So the car is measured relative to earth or relative to ground. So you can't measure the speed randomly. You need to measure the velocity or speed relative to something. That is called frame of reference. Say if, in unit 1, if they see the speed of car is 15 meter per second, so it's moving on ground, and there is an observer. Observer means someone who is doing some measurements. So if there's an observer B standing on the ground, so we can say that the speed of the car on the frame of reference of B. So B is measuring the speed of car. He is standing at rest on the ground. So the speed of the car on the frame of reference of B is 15 meter per second. That word is not used in unit 1. That's the actual way we should say the speed of the car or velocity of the car relative to B, you can say, or speed of the car on the frame of reference of B, because B is measuring the speed of the car. So speed of the car on the frame of reference of B is 15 meter per second. Same way, when there's an observer A inside the car. So if the observer A measures the speed of B, you know, when you travel in a car towards north, you will see all the buildings, everything are moving towards south, is it? You would have seen that. So here I can say the speed of the B on the frame of reference of A, because A is at rest inside the car. he is sitting on the car. So relative to car, he is at rest. So relative to car, he is at rest. So the speed of the car on the frame of reference of B is 15 meter per second. Speed of the person A on the frame of reference of B is also 15 meter per second towards right. Speed of B on the frame of reference of A is 15 meter per second towards left. The car is moving towards right. When A measures the velocity of B, he will say the B is moving towards left at 15 meter per second. So velocity of B on the frame of reference of A is towards left 15 meter per second. Anything could be taken as frame of reference depending on the requirement. Or maybe a ball is thrown vertically upwards. There is a person standing on the ground. He is B. He is throwing a ball vertically upwards at a particular speed. So when the ball reaches a particular height, at that height, the velocity of the ball on the frame of reference of B, B is the observer, frame of reference of B is 20 meter per second upwards. The velocity of the ball on the frame of reference of B is 20 meter per second upwards. At that moment, the velocity of B on the frame of reference of ball, we can take anything as a frame of reference. So velocity of person B on the frame of reference of the ball is also 20 meter per second but downward direction. Like that we can take anything as a frame of reference. Frame of reference means about which velocity of something else is measured. Okay, so now again about relative velocity. B is at rest on the ground. On the frame of reference of B or relative to B, car A is moving towards right at a speed velocity of 20 meter per second. Relative to B or on the frame of reference of B, car X is moving towards right at 20 meter per second. So the observer A, who is sitting in the car, is also moving at 20 meter per second towards right relative to B. Same way, the car Y is moving towards right relative to B or on the frame of reference of B at 12 meter per second. At the same time, the observer on the frame of reference of B, the person C is also moving towards right at 12 meter per second. I think you have this idea symbol. But on the frame of reference of C, the person who is sitting inside the car Y is C. On the frame of reference of C, A is moving towards right at 8 meter per second because both are moving in the same direction. Symbol, even O level they can ask this question, not a big issue. On the frame of reference of C, that is relative to C, A is moving towards right at 8 meter per second because simply every second, 1 second, this will move 12 meters. So this will move 20 meters. So the difference in the distance moved is 8 meters during 1 second. So according to C, A is moving on the frame of reference of C, A is moving towards right at 8 meter per second. On the frame of reference of A, C is moving towards left because the gap is going to increase every second by 8 meters. So on the frame of reference of A, C is moving towards left at 8 meter per second. These are very simple relative velocities. So if A also moving towards right at 12 meter per second relative to observer B or relative to observer B on the frame of reference of B who is at rest on the ground. So if A also moving at 12 meter per second as B in the same as person C in the same direction, X and Y are the two cars. X and Y both are moving at the same velocity 12 meter per second on the frame of reference of B in the same direction if they are moving, then the velocity of A on the frame of reference of C is equal to 0 because there is no change in the gap between the two cars X and Y. So on the frame of reference of C, the velocity of A is equal to 0 or relative to C, velocity of A is equal to 0. Same way, on the frame of reference of A, velocity of C is equal to 0 or on the frame of reference of A, velocity of C is equal to 0. Now if this happens, now the car X is moving towards left at 10 meter per second on the frame of reference of B, that is relative to Earth, we can say. Now what happens? Velocity of A on the frame of reference of C will be 22 meter per second towards Y. Same way, velocity of C on the frame of reference of A is 22 meter per second towards right. So you know, when they are moving in opposite direction, every second the gap will reduce by 22 meters. So the velocity, relative velocity, also 22 meter per second, whether it's relative to C, velocity of A, or relative to A, velocity of C, 22 meter per second, but they will be in opposite directions. Basic principle. Same thing is true for sound wave also. Thing is true for sound wave also. Relative velocity is applicable for sound wave also. Okay, so now think about sound wave. A wave. A sound wave is emitted and it's moving towards left, this direction. So relative to B, who is at rest on the Earth, so relative to B on the frame of reference of B, the velocity or the speed of the sound is 330 meter per second towards him or towards left. Now there's a car moving towards right at a speed of, for example, 20 meter per second on the frame of reference of B. So B is at rest on Earth. So relative to B, the car is moving towards right, or I can say relative to B, the observer A is moving towards right at 20 meter per second. On the frame of reference of B, A is moving towards right at 20 meter per second. So if A measures the velocity of sound, he will say the velocity of sound is equal to 350 meter per second towards left. Because he is moving towards right at 20 meter per second, the sound is approaching towards him at 330 meter per second relative to Earth or relative to observer B, who is at rest on the Earth. A is moving towards right at 20 meter per second. So A will measure the velocity of sound as 350 meter per second towards left or towards him. If the observer A or the vehicle car is moving towards left at 20 meter per second relative to B or relative to Earth, B is at rest, so relative to B or relative to Earth. If the car is moving towards left at 20 meter per second, then A will measure the velocity of sound is 310 meter per second towards him or towards left. The velocity of sound will be different depending on the direction of motion of the observer A. A is moving in different velocities when he is moving towards right relative to Earth or relative to observer B. At 20 meter per second, he will measure the velocity of sound is 350 meter per second towards him. When he is moving towards left relative to Earth or relative to observer B is at rest on the Earth. So the velocity of sound will be measured by A as 310 meter per second towards left. So actually you can ask, is it true? Yes, that's true. The outcome of the change in velocity compared to the actual velocity which is measured relative to Earth, the velocities are different depending on the observer A. That is, the outcome is called Doppler effect. That is called Doppler effect. And the Doppler effect is already discussed it 1 year back. It's there. I will give the link of that also. But anyway, you don't need it. Just I am telling it's called Doppler effect, right? So the speed of the wave also can change, or velocity of the wave also changes depending on the frame of reference. Frame of reference means about which velocity is measured. Okay, now the interesting thing comes here. Earlier I showed it, the speed of the sound changes depending on the frame of reference or depending on the observer. If the observer is moving in different directions, the speed or velocity of the sound measured by the observer will be different. The outcome is Doppler effect. Sound is a wave, so the speed of the wave changes depending on the observer or frame of reference. Now when you think about light, completely different thing happens. Now what they observe recently. When Albert Einstein proposed it, it was not measured practically. So he stated it as a postulate, but I'm going to tell now. But practically now it's confirmed. What the nature the light has means, now the speed of the light is 3 into 10 to the power 8 meter per second, okay, relative to observer B or Earth. Now think about this way. Observer A or the vehicle A is moving towards right at very high speed. Maybe this is 3 into 10 to the power 5 meter per second. He is traveling at 2 into 10 to the power 8 meter per second. What will be the speed of light when A measures the velocity of light? What will be the speed of the light? Earlier we told, when I told about the sound, when the sound travels this way at 330 meter per second sound, and the observer A who is inside the vehicle, when the vehicle moves at 20 meter per second, observer A measures the velocity of sound as 350 meter per second. 330 plus 20, because they are moving in opposite direction, the velocities has to be added, because every second the vehicle will move 20 meter, sound will move 330 meters, so the gap will reduce by 350 meters. So the velocity of the sound measured by observer A will be 350 meter per second. When he moves towards left at 20 meter per second, he has to subtract it, that is 330 minus 2310. If he is moving towards left at very high speed, maybe for example 300 meter per second, practically not possible, but anyway, if you think that 300 meter per second, if he travels towards left and if he measures the speed of sound, he will say the speed of the sound is just 30 meter per second towards him. The difference is the velocity when both are moving in the same direction. Right. Now when you compare this idea with this one, here the outcome is completely different. That means whatever the direction in which A moves, when he measures the velocity of the light, that is electromagnetic wave, that has no change. That will be exactly the same as 3 into 10 to the power 8 meter per second. If the observer moves towards right at 2 into 10 to the power 8 meter per second, or even when he moves towards left at almost 3 into 10 to the power 8 meter per second, whatever the direction A moves, the velocity of the light measured by A will remain the same. That means very important conclusion which was not used in classical physics. This is the basic main fundamental postulate used in special theory of relativity. Because of this postulate, but anyway it's confirmed later, because of this postulate only all the new unbelievable outcomes came in or proposed by special theory of relativity. What it says, the speed of light is unique. It does not depend on any frame of reference. Whoever measures the speed of light, that will be the same. For example, if the observer A moves towards right at 3 into 10 to the power 8 meter per second, you would have heard nothing can travel at speed of light, but we assume if he is traveling towards right at 3 into 10 to the power 8 meter per second, he will measure the speed of light as 3 into 10 to the power 8 meter per second. It won't be 6 into 10 to the power 8 meter per second. But here if the sound is, the observer moves towards left at 330 meter per second, he will measure the speed of sound as rest, 0 meter per second. But here, if the observer A moves towards left at 3 into 10 to the power 8 meter per second, we know that nothing can travel at speed of light, but we'll imagine in case if observer A moves towards left at 3 into 10 to the power 8 meter per second relative to ground, here the speed of light measured by A won't be equal to 0, but here for sound it could become equal to 0, but here the speed of light measured by A, it remains same as 3 into 10 to the power 8 meter per second. There is no change in speed of light or speed of electromagnetic wave relative to a frame of reference. That is the very basic fundamental idea or postulate used in relativity. That is true, experimentally confirmed. So because of this nature of light, there are a lot of outcomes in the understanding of space, time, mass and energy. Unit 4 you learn that delta E equal delta mc square or E equal delta mc square, that is mass deficit into c square. How this happens? Yes, because of this postulate. Here we are going to use two more outcomes of the special theory of relativity. Those are the time dilation and length contraction. I am going to explain that now. Okay, so one of the conclusion or outcome of special theory of relativity, E equal mc square, you learned that in unit 5. In radioactivity, also you use that in particle physics. Okay, now next thing is the time dilation. What is it? The time dilation means the time taken for any event in a moving object will slow down when it is observed from an observer outside the moving object. What do you mean by that? Say for example, we'll think like event means what? Anything. Say for example, event means when you think about clock, the second hand moves from here to here. That's an event. Event means the ticking off every second is an event. Or maybe anything. Say for example, another thing I can say as an event. There's a light, something like a light that emits light, like a pulse of light is emitted from a bulb every 5 seconds. It's an event. So the event happens at every 5-second interval. What is the event? Emission of pulse of light. Emission of pulse of light is an event. So I can say the event, which that means emission of pulse of light happens at every 5-second interval. I can take it as an event. Or maybe even a chemical reaction. That means, for example, if you have a beaker, it consists of a particular chemical which is transparent, no color. Now when you add a drop of another chemical into it, the color changes. How long will it take for color to change after dropping a droplet into the chemical? Maybe 2 seconds. So that is an event. Every 2 seconds, that means it's an event. That means an event means when a chemical X is added to chemical Y, in 2 seconds the color will change from transparent to a particular color. It's an event, right? So like that, any event that happens in a moving object, and if it is observed from outside the object, person who is observing from the outside the object will feel the events happening in the moving object is slowing down. That means they are taking longer time. That's the way the theory of relativity, the time dilation explains. We can derive these things, but you don't need. For example, imagine there's an observer. Is observer B standing on ground, and he has a clock. He's holding a clock. It's analog clock or digital clock. There's a vehicle. Inside the vehicle, there's an observer. He is also having a clock. Identical clocks. Both are identical clocks. They are synchronized. Synchronized means both clocks function or ticks exactly the same way, nothing different. And there is a bulb inside the vehicle. So when the vehicle is at rest, the bulb emits pulse of light every 5 seconds interval. So the time period of the event of emission of light is 5 seconds. So the vehicle is at rest. There is an observer A inside the vehicle. He is having a clock C2. There's a clock C1. B is at rest on the ground. A is inside the vehicle. Vehicle is at rest. Both have identical clocks. C1, C2 are identical. They are synchronized. They will function exactly the same way, the second hand sticks. And there's a lamp which can emit light, pulse of light, every 5 seconds when the vehicle is at rest. Okay, now what's happening? Now the vehicle is started to move suddenly, quickly. It started to move at a very high speed, almost 0.7 times of speed of light. Now the vehicle is suddenly moving at very high speed, that is 0.7 times or 70% of the speed of light. Now what's happening? The person who is standing on the ground, on his frame of reference, I can say, already I used that word frame of reference. So the observer B is observing the emission of light. He is observing the emission of light, how long it takes to emit pulse of light. Earlier, when the car was at rest, he measured the time. 5 seconds is the period. Every 5 seconds it emits light. He also measured when the car was at rest, the light emitted at every 5-second interval. Now, when the observer who is on the ground, when he observes the light emission from the lamp which is inside the moving vehicle, he will measure according to his clock. He is holding a clock. The two clocks were synchronized earlier. Now he is measuring the time interval between the pulse emitted from the bulb. He will measure now the time is not 5 seconds. It will be longer than, greater than 5 seconds. We can calculate. There's an equation for that. That means he will argue, the B will argue, when the car moves at very high speed, almost at the speed of light or 70% of the speed of light, the event, that is emission of light, pulse of light from the moving vehicle, is delayed or slowing down, or there is time dilation happening. He will say like that, because now the time measured by B, by using his clock, he is measuring, okay, now he is seeing the pulse of light, okay, then next pulse of light he is observing. So the time interval he is observing after seeing the first pulse of light, the time interval according to his clock C1, he is measuring the second pulse of light when he is seeing it, that is more than 5 seconds. But the weird thing here, when A observed the light, he will say the light is emitting same as earlier every 5 seconds. He will say, the observer A will say that bulb is emitting the light same as earlier at 5-second intervals. There is no change in the time interval between the events. It's happening exactly same as when I was at rest, it emitted every 5 seconds. Now also emitting the same time interval at 5 seconds. He will feel the same according to his clock when he measures. That means I can give a conclusion. When the vehicle moves at higher speed, which is closer to speed of light, the time taken for any event will get longer. That means I can say the events happens slowly, or I can say there is time dilation in the measurement of events, or the time interval between the events. That is the important conclusion, I should say, related to special theory of relativity. Not only light flicking, any event, even a chemical reaction I told earlier, that means when the droplet, when you put a drop into chemical X, when you put a chemical Y droplet into chemical Y, I told earlier, when the car was at rest, if you had the same thing, from the moment the droplet is released, in 2 seconds the color changes. Now when the vehicle moves, if the same event happens and if we observe that, he will say the color change happens from the moment the droplet is released. Color change happens not at 2 seconds, more than 2 seconds. That means any event will take longer when it is observed from an observer outside the moving vehicle. It will take longer. But the observer inside the moving vehicle, he will have no change in the time measurements between the events. The observer A will say there is no change in time measurement, it remains the same. Why all this happens, anyway, you don't need, that is based on special theory of relativity. But what is the reason for these things? Why don't we feel that when the speed is not much higher, Do we feel that in our day-to-day life? No, we don't feel, because day-to-day life the speed at which the vehicles moves are not closer to speed of light. And what is the root, the reason for this to happen? Because the speed of light is the same at all frame of reference. That's the reason. Okay, so there's an equation for this time difference measured by observer B compared to the time interval between the events. So the time measured by B, which is t, is given by the time measured by A, or the time interval between the events measured when both were at rest, when the car was at rest. If I say that is t over square root of 1 minus v over c all the square. Not in your syllabus, I am just using it to explain more clearly. That means the time interval measured by both A and B when the car was at rest for the event of emission of pulse of light is 5 seconds. So even now the A measures the time interval between emission of pulse of light is 5 seconds, but B is measuring different time, so that measured by B, TB, that B measures the time of event happening inside the vehicle. That is 5 seconds is the time actually it was measured when both were at rest, or still it's measured by A over square root of 1 minus the speed of the vehicle is 0.7 c, 0.7 c over c all the squared. So if you solve, you will get that is 7 seconds. So that means the observer B, or according to the frame of reference of B, the time interval, which is emission of pulse of light, happens at every 7 seconds, not at 5 seconds. That means the event is slowing down. The time taken for the event is getting longer, or there is time dilation. So that means not only for the emission of light, for any even for chemical reaction or even for biochemical reaction happens in the living organism, everything will take longer when it is observed from outside the moving vehicle. But the observer inside the moving vehicle won't have any change in the measurement of time. Okay, so one more conclusion based on theory of special theory of relativity, that is length contraction. That also we need to explain the motion of muons, how they were able to reach the bottom of the mountain. I need to use the length contraction, but nothing in your syllabus related to that. But if I want to give full complete explanation, I need it. Okay, so the length contraction means, imagine there's a rod that has a metal rod that has a length of 100 meters. So there's an observer on the ground, B. So the rod is at rest and the observer also at rest. So when he measures the length, both are at rest. So normally when you measure the length of this thing like that, when he measures the length of this rod, he will measure it as 100 meters, nothing wrong. Now what happens, the rod is thrown or projected at very high speed. Imagine it's projected at speed of 0.7 times of speed of light, 0.7 c, it's projected at a speed of 0.7 c, the speed of light c. So v is equal to 0.7 c, that is the rod is projected at a speed of 70% of the speed of light. This is rod. Now B is measuring, B is at rest on the ground. So on the frame of reference of B, he is measuring the length of the rod when it is in motion at 0.7 times speed of light. Maybe he might be using some sensors or whatever, we don't know, we don't need to think about it. But he is measuring the length of the rod. What happens? He will measure the length of the rod when it is in motion. He will measure the length is smaller than 100 meters. He will measure the length of the rod which is smaller than 100 meters. He won't measure it as 100 meters when the rod is in motion at 0.7 c relative to B, or on the frame of reference of B. the rod is moving at 0.7 c, then the length will become smaller than 100 meters. For that also, there is an equation derived and obtained in special theory of relativity. So that says L is equal to L naught square root of 1 minus V over C all in square, not in S syllabus. Just for your understanding I am doing it. So there if you substitute, L naught is the length when both are relatively at rest. He is at rest when the rod also at rest. When he measured it as 100 meters. Now what length he will measure when it is at motion? The length measured by B, 100 into square root of 1 minus 0.7 c over c all in squared. So the observer B will measure the length as, it will measure as 71.4 centimeters. 71.4 centimeters, which is lower than 100 meters. 71.4 meters, sorry, 71.4 meters, which is lower than 100 meters. So this effect is called length contraction. Relative motion causes, when the motion is at very high speed, closer to speed of light, there will be length contraction. But we don't feel these things day-to-day life. For example, imagine this is a rocket which is traveling at 500 meters per second, very high speed. Or maybe when you think about something like a geostationary satellite or something like the maximum speed what we can reach in our day-to-day life, something like 4,000 meters per second. Substitute 4,000 meters per second. This has 3 into 10 to the power 8 meters per second, and find it. You will get all same answer 100. So day-to-day life we don't feel these effects unless it travels at a speed closer to speed of light. Day-to-day life we don't feel these things. Okay, so the same way, imagine there is a car. There is an observer A inside the car. The car was at rest and there is a rod kept on the ground, that is 100 meters. Rod is at rest, car is at rest. So A is measuring the length of the rod. He will measure it as 100 meters per second. The rod is at rest relative to Earth or relative to another observer B who is at rest on the ground. So B is at rest on the ground. So there is a rod that also at rest relative to Earth. The car A is also at rest. The car X, inside there is a passenger A or observer A. They all are at rest relative to Earth. So when A measures the length of the rod, he will measure it as 100 meters. Now what happens? A is moving suddenly at very high speed, which is 0.7 c. The rod is not moving 0.7 c. The observer A or the car X is moving at a speed of 0.7 c. I told that. So when the car moves at 0.7 c towards right relative to Earth or on the frame of reference of Earth, car is moving towards right at 0.7 c. On the frame of reference of Earth or relative to Earth, the rod is at rest. Relative to A, careful, relative to A or on the frame of reference of A, the rod is moving towards left. Velocity of rod relative to A or on the frame of reference of A is 0.7 c towards left. You know that when the car moves towards right, he will feel the rod is moving towards left at the velocity of 0.7 c. But relative to Earth, the rod is at rest. It's not moving. But A is moving towards right with the car at a speed of 0.7 c. Now what is happening? Relative to A, the rod is moving, or on the frame of reference of A, the rod is moving towards left at 0.7 c. Now by using a sensor or something, A is measuring the length of the rod. When A measures the length of rod, he will measure it as the length has contracted, because on the frame of reference of A or relative to A, rod is moving towards left at 0.7 c. Now when LA, the length measured by A is equal to L naught square root of 1 minus V over C all things squared. So when A measures the length, he will measure it as same as earlier what I calculated 0.7 C over C all things squared. He will measure the length of rod. A measures it as same as earlier 71.4 centimeters. So he will say the length of the rod has contracted, it has become smaller. But when B measures the length of rod, B is at rest relative to Earth, rod is at rest relative to Earth. So rod is at rest on the frame of reference of B. B will measure the length of rod as 100 meters. No change he will say, but A will say the length has decreased. I am going to use these ideas to explain how Muon was able to reach the ground by falling through a distance of 1600 meters. The question January 2021. These ideas I am going to use there. Anyway, exam view I already explained when I started this lesson. Based on exam, that is enough. You will get the full marks. But just I am explaining all these things for the students, those who want to know the reality, what is time dilation, why that happens. But by using time dilation alone, I can't explain fully the motion of muon. I need to use little bit of idea related to length contraction also. These are the conclusions or the outcome of special theory of relativity. Okay, so this January 2021 question, which is a 5-mark question. Before that, they are saying in that question the lifetime of muon is 2.2 10 to the power minus 6 seconds. So imagine the muon is falling from top of the mountain to the ground. So rather than thinking of muon, I can imagine muon is falling down or moving down at a speed of 0.994 C, and that speed is moving there, say. So rather than thinking only the muon is falling down, I can imagine the muon is kept inside a rocket. Imagine that a muon is kept inside a rocket. This is the rocket. The rocket is moving at a speed of 0.994 C. Relative to the observer who is on the ground, he is observing these events. The rocket is moving down at 0.99 C. There is an observer A inside the rocket, and there is a muon inside the rocket. So relative to observer A, the muon is at rest. But relative to observer B, the rocket is moving down at 0.99 C, means muon also moving at 0.99 C. I already told that when a car moves towards right, relative to observer A, there is a car, there is an observer here, there is a clock or whatever it is, there is an observer B. If the car moves at 20 meters per second, relative to observer B, the clock also moving towards right at 20 meters per second. The observer A also moving at 20 meters per second relative to observer B. The observer, there is no need for A to move outside the vehicle or anything. He is inside the vehicle. Vehicle is moving 20 meters per second. Relative to B means the observer also moving at the same speed. So here there is a, the question says a muon is moving down at 0.994 C. So to make it more clear, I am taking the muon is inside a rocket. The rocket is moving down at 0.99 C, and the muon is at rest inside the rocket. So relative to B, muon is moving at 0.99 C. So there is relativistic effect relative to the frame of reference of B or relative to observer B. But observer A, if he measures the lifetime of the muon, the observer A will say the lifetime of muon, it's an event, lifetime. The muon is created, then it becomes energy, it decays. The time interval between the creation and decay is called the lifetime. So when A measures, who is inside the rocket, when A measures the lifetime of the muon, he will say the lifetime is 2.2 10 to the power minus 6 seconds. It's an event. It's an event. I told that earlier. When a car moves, there's a light, there's an observer. When the observer measures the time interval between the flick of light, he will measure it as 5 seconds. In my earlier example, same way, when observer A measures the lifetime of the muon, the time interval between creation and decay, he will say that is 2.2 10 to the power minus 6 seconds. But observer B, the scientists on the ground, they are measuring the time taken by the muon to reach the ground. So they will say the muon or the rocket moving at 0.994 seconds. So the observer B will argue time taken to reach the bottom of the mountain that is T is equal to speed equal distance over time, time equal distance over speed, that is 1600 meters divided by 0.994 into 3 into 10 to the power 8. They will say the time that is needed to reach the bottom for the muon or the rocket or A, the observer A to reach the ground, that will be equal to, they will say the required time will be equal to 5.37 10 to the power minus 6 seconds, which is greater than the lifetime of the muon, 2.2 10 to the power minus 6 seconds. So according to observer B, he will argue the time that is required to reach the ground from the top of the mountain for the muon is 5.37 10 to the power minus 6 seconds, which is more than the lifetime. So before it reaches the B, it will decay, it will become energy, so the muon won't be there. But what happened? They detected the muon at the bottom, means muon is able to reach the bottom without decay. How is it possible? That's a question. Now look at here. The 2.2 10 to the minus 6 seconds is the lifetime when the muon is at rest relative to an observer. So relative to A, muon is at rest. A will say the lifetime is 2.2 10 to the power minus 6 seconds. If the muon was at rest closer to B, B will measure it as 2.2 10 to the power minus 6 seconds. But now the muon is moving inside a rocket at a speed of 0.994 seconds. So the time taken for the event of decay won't be 2.2 when measured by B. So actually if we measure the time of decay or the lifetime of muon, if B measured, lifetime of muon measured by B won't be 2.2 10 to the power minus 6 seconds, it will be different. So I can find that here, lifetime measured by B that is equal to measured by B, that time taken for the event, that is going to be T when it was at rest over square root of 1 minus V over C all things squared. This is 2.2 10 to the power minus 6 seconds when it is at rest relative to B, but it's in motion. So if the B measured the lifetime, he will get measure that lifetime will be, which is equal to 20.1 10 to the power minus 6 seconds, which is much larger than 2.2 10 to the power minus 6 seconds. So actually now we should say, okay, when it is moving in a vehicle or when the muon moves at a speed of 0.994 c relative to B, the lifetime is getting longer. The lifetime is becoming larger, which is 20.1 10 to the power minus 6 seconds compared to the lifetime when it is at rest related to an observer. This is longer. Therefore, it is able to reach the bottom of the mountain. The observer B will say. Okay, so B is saying that its lifetime has increased, not 2.2. According to theory of relativity, yes, the lifetime has become more than 2.2. The time taken to reach the bottom, I calculated earlier, speed equal distance over time. The required time to reach the bottom is 1600 over 0.994 into 10 to the 3 into 10 to the power 8. So the actual time required that is equal to 5.37 10 to the power minus 6 seconds. So this is the time taken by the muon to reach the ground when measured by V, but the lifetime is now 20.1 10 to minus 6 seconds. So this time is smaller than the lifetime. So we will say the time taken by the muon to reach the ground is 5.37 10 to the minus 6 seconds. When I measure the event of lifetime of muon, it has become 20.1 10 to the power minus 6 seconds. So the time taken to reach the ground is smaller than the lifetime of the muon, so it can reach the bottom before it decay. We will say the conclusion. Okay, we will be happy now. He said that's the reason happened according to relativity. Yes, that's right. Now the problem is, if you ask A, he will say, the observer A who is inside the vehicle, the rocket, he will say the lifetime is remaining the same, 2.2 10 to the power minus 6 seconds. So if you ask observer A, how were you able to reach, how the muon inside the rocket is able to reach the bottom, because its lifetime is 2.2 10 to the power minus 6 seconds. The time required to reach the bottom is 5.37 10 to the power minus 6 seconds, which is larger than the lifetime. How the muon can reach the bottom of the mountain, if you ask, then the observer A will say different answer. Yes, according to him, there is no change in lifetime. That remains the 2.2 10 to the minus 6 seconds. So he will say, okay, we are not going down, we are not moving down 1,600 meters compared with the example what I told, when the car moves at 0.7 C, there's a rod which is 100 meter. If we measure the length of the rod, that is smaller, not 100 meters, it will become 71.4 meter. I already did it. Same idea, length contraction. So observer A will say, yes, we are falling down. The lifetime of the muon is 2.2 10 to the power minus 6 seconds. There is no change. The time taken is not this time, because we are not falling down 160 meters. We are falling down, or we are moving down a shorter distance than 1,600 meters. How much is he moving down? If he measures the height of the mountain or the distance he needs to move down, if observer A measures, he will measure LA is equal to L naught into square root of 1 minus V over C all things squared. So he will say, the observer A who is moving with the muon, he will say the lifetime is same, but the distance we are falling down is 1 minus 0.994 C over C all things squared. So if he measures it, the distance he is going to fall down is equal to, that will be equal to 175, much smaller, 175 meters. That's all. He will say we are not falling down 1,600 meters. Sorry, we are falling down just 175 meters. Its lifetime is remaining same as 2.2 10 minus 6 seconds. We are falling down at this time. So we are going to take time. How long we will take to reach the ground to fall 175 meters. So time measured by A is going to be distance 175 over speed 0.994 into 10 to the power, into 3 into 10 to the power 8. So A will say we are going to move down 175 meter, not 1,600 meter. The lifetime of the muon is no change, 2.2, but we will take a time that is equal to 0.587, 0.587 into 10 to the power minus 6 seconds, which is much smaller than lifetime of the muon. So we will reach the ground before it decays. See, both are explaining. Observer B is able to explain by using the increase in the lifetime, time dilation, but the observer who is traveling with the muon, he will explain no change in lifetime, but the distance we are moving down is not 1,600, we are moving 175 meters. So we will take only this much of time to reach the bottom, which is smaller than lifetime, which is measured by A is 2.2 10 minus 6. So we are able to reach the ground before it decays. So both sides are able to explain. Observer A, who is moving with the muon, or I can say it's in the frame of reference of muon because both are moving together, frame of reference of the muon. The lifetime of the muon remains the same, but the muon is falling down a length or height which is smaller than 1600 meters. The time required is smaller than the lifetime. When scientists on the bottom of the mountain, when they measured observed the motion of the muon, they observed the lifetime of the muon is not 2.2 10 to the minus 6 seconds, which is long. I calculated and erased it, which we got earlier. The lifetime is 20.1 10 to the power minus 6 seconds. So they are able to reach the ground because time taken is 5.37 10 to the minus 6 seconds. The lifetime measured by B, TB, capital T, is 20.1 10 to the power minus 6 seconds. So the time required to reach the bottom is smaller than lifetime. So muon is able to reach the bottom, we will say. See, anyway, we can explain, but too much for A-level students. So I did this only for the students, those who want to know the actual thing. Don't write these things in the exam paper. For the answer that should be written in the exam paper, I already explained or stated when I start the lesson, this one. Okay, so that's fine. I hope you understood the meaning of special theory of relativity. I explained in a way that A-level student can understand. I didn't go in detail of it. I already done complete lesson on particle physics, magnetism, circular motion, and 12 lessons in electric field. So you can go through them. I'll give the link. Those are completely focused on Edexcel exams. I will give the link or the URL for them in the description of this video. Bye.